Hi everyone, welcome to Exam 2 review. I'm just going to go over each one of these sections that were mostly covered by the reading slides, the required reading for each lesson. So we'll start with hardware. For the hardware components of a computer, you're primarily looking at the CPU, the main memory, and secondary storage. So the CPU, that's the brain of the computer. It runs or executes programs, and at the lowest level, it understands binary instructions. So any high-level programming that programmers do gets converted into ones and zeros, which is and even more than that, those ones and zeros get converted into binary numbers, which are 8-digit arrays that are understood by the computer to run programs. Then there's main memory, which consists of RAM and ROM. RAM stands for random access memory, and it stores the program while they're in running or in execution mode and the related data. It's erased when the computer is turned off, so that's why it's called volatile memory, because it's only there when the computer is running, and if something happens to the computer, for some reason it loses power, all that information is wiped. In comparison, ROM, which is read-only memory, is non-volatile. It doesn't get lost when the power is turned off. It's stored somewhere on the computer where the computer can read it, but it cannot change it. And so programs that are vital to a computer's operation are stored in the ROM. Next up, we have secondary storage. So you could think of it like a hard drive or a solid state drive. These storage spaces hold data for long periods of time, even when the power is turned off. And so if you put something on your hard drives, you know that when you turn a computer off, those documents or videos will still be saved on the drive until you boot the computer back up again and want to use it later. The smallest storage location on a computer's memory is known as a bit. We'll dive into that in a second here. So storing data. All data is converted in a computer to ones and zeros. The memory is divided into tiny storage locations called bytes. 1 byte represents a number. And so all programming that's high level, like I was saying earlier, gets converted into bytes, ones and zeros. And then further down, each byte is represented by 8 bits, which are binary digits. Next up, we have ASCII 2. So ASCII 2 is a form of language character representation. And that is how characters are represented in a computer's memory. You can also call it a coding scheme. And it is a set of 128 numeric codes, and each one of those codes represents a character. Next up, we have how programs work. So when a programmer starts to write code, they'll plan out the program using pseudocode, where programmers don't really have to worry about syntax rules. So pseudocode is, pretty loose. It doesn't follow any structure per se. No one's going to come at you if you have a space in there in your variable name in pseudocode or something like that. It's just for planning out, say I'm writing a program for what I need to do before I leave. So, I could write something like do eat breakfast, do get load, do get the keys, etc. So this can be, in a language that any human can read and understand, and you don't have to worry too much about syntax and compiler errors. You just get coding, so you can plan out the program. And then after that, you convert the program into source code, which is, in a way, y'all have been doing that in Flowgorithm, where you're converting the pseudocode that is provided in the homework manuals into the Flowgorithm flowcharts. And so those flowcharts, in a way, are pseudocode. But normally pseudocode is written by programmers in a high-level language like Java, Python, etc. And then syntax or rules that must be followed when writing a program. And so you might have noticed when you put a space in the variable name, Flowgorithm might have an issue, or when you do certain things the wrong way, Flowgorithm doesn't actually compile the program, right? It gives you an error of some sort. And those are syntax rules, and they're even more picky with programming languages. Next up, we have variables. So variables are a storage location in memory that is represented by a name that can hold different values during a program's execution. So we've had plenty of practice with variables so far with the assignments and labs. You know that to use a variable, you must first declare it like this. So you write declare, and then this is in the Flowgorithm language. So you write declare, and then you pick the data type for that string or the variable, and then you give it a name. So there's the name and the data type. That's what you need when you're declaring a variable. And then declaring basically just means you're allocating the memory for that variable. So you're in a space on the computer, you're creating, a spot where you're saying, okay, I'm going to create a variable called student name, and it's going to hold this type of data. I'm actually going to move this down to data type so I can go over that appropriately. Okay. So yeah, before we can use a variable, it needs to be declared, and then it's declared like this. But just in the Flowgorithm language, every language has kind of its own way of declaring variables. Another way, a common way to write the variable names is with an underscore instead of a space. You can never use spaces for variable names because the program, when it's parsing this to understand what it is, if there's a space, it doesn't understand whether you're declaring two variables, which could be something that other programming languages use or what. So we don't have spaces in variable names. They're either connected using an underscore, or you don't have anything between the two words. And so if you're using common camel case, which is a common convention for variables, you'll have the first word is completely lowercase, and then after that, every word after has its first letter capitalized. So that's what camel case is. I believe the idea is that this is the hump of a camel. So student name right here is in camel case. So everything is small on the first word, and then you have a capital first letter on the second word. Can't include spaces, and then you cannot use a variable without declaring it. So you can't just set student name to something without having declared it first. I'm sure you ran into this on Flowgorithm. Next up is data types. So you can assign a variable to one of these three data types in Flowgorithm. There's many more, but for now, we'll just focus on these basic ones. So integer, which stores only whole numbers. So whole numbers would be, 2 or 100, anything without decimals. Real means whole or decimal numbers. So real can store 2 or 2.5 or 1000.467, any decimal number. This is also called floating point number or floating point notation, which is what is used to encode real numbers to store them in computer's memory. So that's a programming term. And then we have strings. And strings is any series of characters, but you'll normally put quotations to mark the beginning and end of a string. So yeah, I'll show you down here. So programming has quotes at the beginning and end, so now it's a string. So if you have something like 1, 2, 3 in here, this is not a integer or a real number. This is a string. So anything with quotes around it is a string. And you can't do mathematical functions on this because strings are considered like text or characters. Variable assignment. So once you've declared a variable up here, you can now assign it to a value. So you can now say set that variable to a Latin. And now it'll hold a Latin. And then later on, you could set student name to somebody else and it'll change. So the variable value can be changed once declared, but it must be declared before. Same with integers, you can set them the same way. Set variable name equals a value. Same with reals, set real. And again, real can hold whole numbers as well. These are some rules. So integers cannot store a floating point value. So you can't set an integer declared variable to 98.1. That's an error. You can't set a string to an integer value. So you can set a string to quote 1, 2, 3 quote, because now we've turned this into a text string, but you can't set a string to 1, 2, 3 without the quotes because that's a number. That'll fail. Lastly, you can't set a string to a floating point value. So you can't set a string to 98.1 either, unless it has quotes, at which point it's no longer a number, it's a string. Uninitialized variable, so to avoid errors, you should set variables to something once they're declared, because if you don't set it to anything, then you're not exactly sure what you're working with, and sometimes they could be set to null, blank, 0, where we don't know. Different programming languages do different things, and so it's better just to know exactly what you're using, and you should always set a variable to something after declaring it. Not doing so will induce a logic error, and so logic errors are different from compiler errors or runtime errors because they don't keep you from hitting run on the program. You might have noticed some of those errors. Your program doesn't even run, so that would be a compiler error. A logic error is where the program runs fine, but there's incorrect results. So if there's a problem with your calculation or your variables, that's called a logic error. Next up, we have calculations. So they can be performed using math operators, just like we use in algebra or something. So set sale equals price minus discount makes sense. Whatever the discount is, take that out from the price and set sale to the value of that. And we can also use parentheses to change the order. So, if you didn't have parentheses here, 10 would be divided by 3 first. And then 3 would be multiplied by 4. This is a multiplication symbol in programming. And so because we have parentheses, we're adding 8 and 10 first, which means that's 18. Then we're going to divide 18 by 3, which is 6, and then we're going to multiply it by 4, which is 24. The result is 24. So adding parentheses can change the order of calculations, just like in math. A named constant is kind of the opposite of a variable. So a variable can be changed. The value for a constant cannot be changed. And so if you have a program and say you're calculating mortgage rates or mortgage calculations, then the interest rate might be an important factor to you. And you might be using that interest rate all over your program. But say you have to change it later. You then have to change it in every single spot that interest rate was used. But if you create a constant, a named constant, so constant with the name interest rate and the data type real set to 0.06, now you only have to change this value, and then it'll update wherever interest rate is used. But you can only change it up top where it's being declared. But it can't at the same time hold two different values like a variable can. Next up is decision structures. And so the beauty of programming is that it's dynamic, right? Based on different inputs, we can execute different types of statements. And so it's the opposite of a sequence structure. A sequence structure is, each statement gets solved line by line. So earlier when I made that example of what do I need to do to get ready for the morning, do eat breakfast, do this, do that. Those are all going in sequence and there's no decision taking place. However, a decision structure, in contrast, allows a program to perform actions only under certain conditions. And that's the diamond symbol used in flowcharts to denote decisions. So we have different types of evaluations we can run. We can add an if statement where, if the condition is true, then an action occurs. Or we can have a if then else statement. So if it's true, something happens, otherwise something else happens. You can also have a if then else if. So you can keep adding else ifs, which means you can compare many different conditions, and then if none of those are true, then it'll go to an else. You can also nest it to test more than one condition. So if something is true, but then if something else, so you could do like if it's cold, and then it'll go into this statement because that's true this morning. We could put if it's nighttime. Now it's nested. So for this statement right here, wear a jacket, a reflective jacket. Now this is nested because this is further into it being cold. So if it's cold and it's nighttime, then wear a jacket, a reflective jacket. You could also combine these by using an operator, which we'll go into next. But if it's cold, whoops. And if it's nighttime, then wear a jacket, and that's the same thing. Okay, next up is relational operator. So if you're dealing with numbers, real or integers, you can compare them in the if statements using greater than, less than, equal to. Pretend there's no space here. When I use this tool that I'm using right now, it combines. Oh, I didn't do it here. Sometimes it doesn't like me adding spaces. If I add spaces, it'll turn these symbols into something else. But there we go. So greater than equal to, less than or equal to, not equal to. And then equal to is two equal signs. And then in some languages, you can also compare two variables. So say student name is set to Aladdin. You can put an equal and compare it to another variable, say, teacher name equal Aladdin. Now you're checking to see if any students have the same name as teacher. You can compare two variables, their equivalents, using two equal signs. You can also test to see whether they're not equal by adding an exclamation point and an equal sign. So this means not equal to. Next up is what I was talking about earlier. You can combine two checks or two decisions using and or not. So if it's cold and it's nighttime, both of these must evaluate to true for us to go further. So and requires both conditions to be true. So if one is true and one is false, then it'll say this is false. The whole string or the whole decision evaluates to false and it won't go into this statement. It'll just move forward. In contrast, or requires only one to be true. So if I put or here, it's going to go down to reflective jacket, whether it's hot or cold as long as it's nighttime, or whether it's nighttime or daytime as long as it's cold. So or evaluates whether, regardless of whether one condition is false, it just needs one condition to be true. So if any condition is true, the statement will evaluate to true. Next up is not, which reverses the expression. So if we add if not cold, go to the next, go evaluate this statement or run this statement. And so it'll only run this if it's hot, right? Which is the opposite of cold. So not true evaluates to false. If the expression is false, then the not operator will return true. So basically, if it's not cold, it'll always return hot. It's also called a unary operator because it only needs one. So before with and or we were combining multiple decisions together. With not, there's only one decision. They're also called short circuit evaluation, ands and ors, because if the first expression is false, then the right is not tested because you need both to be true for it to evaluate to true. So it short circuits. So if the left is false, or if the first condition is false, and will always short circuit. Or only needs one to be true. So if the left is true, or the first statement is true, then it'll always evaluate to true. It doesn't need to test the other conditions. All right, Boolean functions are used to validate data, so form data that could be dirty or could have incorrect data in it. We often test with a lot of Boolean functions. So, did the user submit a string? Does a string have characters in it? How long is the string? Is it too short? Say like a password requirement. So if you force the user to set a certain type of password, we then validate that password using many different decision structures and Boolean functions. Here's just some examples. So if the temperature, oh yeah, okay, so say the temperature is 40. If the temperature is greater than 60, it's not, so we'll move on. Is the temperature less than 40? 40 is not less than 40. 40 is equal. So it'll go into here actually. So since we didn't put less than or equal to, this is what I was saying. So my tool right here turns a greater, less than or equal to sign automatically to that. But there you go. Okay. So let's set these as equal to's. Greater than equal to. Okay. So what displays for 40? Well, 40 is greater than is less. So it'll only go in here if it's greater than 60. So display sunny morning, it'll be displayed for 65 or 80, right? Oh, then we have an hour too. So let's assign an hour as well. So as long as the hour is less than 12, so we're passing in two variables. We're passing an hour and a temp. And so usually in decision structures, what I'm trying to show here is that the first decision that's satisfied as true, that's the one that gets executed, not any other ones. And actually these were just for this example. So I'm just gonna undo what I was doing here. Okay, yep, so this will only print if the hour is less than 12, which means it's before noon, and temperature is greater than 60, it'll print sunny morning. So temperature is less than 40, so this will evaluate for either 25 degrees or higher than 80. But for this, both of these conditions need to be true, whereas for this, only one. So if the temperature is 25, it'll go in here. Or if the temperature is 100, it'll go in here. Unless we put an else. So if we don't put an else, then it'll do this and then it'll do this. However, if you put an else, actually these are two separate statements. So if the temperature is, yeah, let's just go over what this one means. So let's consider this separate because it won't go in here as long as this statement exists, unless we do and temperature is less than 100. So now it won't go in here if it's greater than 100. And how does this one resolve? So If not, temp is greater than 100. So yeah, you kind of have to use your brain here a little bit. So temperature greater than 100. So if we pass in 110, is the temperature greater than 100? Yes, but then it flips it. So it'll only go into here if the temperature is not greater than 100. And so it flips this logic, basically turning this into this. So using a not is the same as having, the opposite condition. So as long as the temperature is less than 100, it won't be boiling today. Yeah, let's evaluate these real fast. So 40, if the temperature is less than 40, less than 60, yeah, it's 40, so that's a little cold. 80, 80 is not less than 60, so it doesn't go in here, it goes in here. 80 is greater than 75, wear shorts. Else 65, so 65 is not less than 60, 65 is not greater than 75, it'll go into the else, which is must be a nice day. Next up, we have repetition structures, and so we use these in the last few algorithms where we repeated a certain condition repeatedly as long as a condition was not met. And so with all loops, be careful not to create infinite loops. I saw this in some of your homeworks where the loop never ended, and so the computer kept running the statement again and again and again, and that can cause the computer to use up a lot of resources, memory, and space, depending on how the program was written. In a loop, you have what's called the test condition. So in this case, the test condition is until k is greater than 3. So until that happens, it'll keep looping, and then this is a loop body. So the statement's actually being executed. And so statements inside a loop are called a loop body. Test conditions can use any variable type, and so strings, integers, reals, they can test any of those variables. You have two types of loops. We have count controlled and condition controlled. Conditions rely on a Boolean condition to break out of the loop. And so keep doing this until the temperature is 100. That's a condition control loop. There's three types. There's while loops, where while the condition is true, do something. So these ones test the condition and then do something. Contrast, we have do while, which does something and then tests the condition. So if you want to do the action first, then test it, which means you want to run it before checking the condition, you do a do while, which is also called a post test because the test is after running the loop. And then lastly, we have a do until. So do until does some task until the condition is satisfied. So k starts with 1. So display k, so 1 is printed to the screen, and then we bump the value of k by 1, which means k is now 2. Is 2 greater than 3? No. So we see on the screen 1. Next, k is now 2. 2 is printed, and then 1 gets added to 2. K is now 3. Is 3 greater than 3? No, it's not. Goes back in there. 3, k is now 3. Actually, it doesn't go all the way up here. It actually goes up here. So k is displayed as 3. Now k is 4. Is 4 greater than 3? Yes, it is. It'll stop. So k will print 3 times. So that's how you kind of run through a loop. It can be used to iterate the body of a loop a specific number of times. Over here, we said don't run this, more than this many times in a way by setting up a counter. While loops will run infinitely when there's no statement that will make it false. And so, if we didn't have this adding to k would always stay as 1 and it would never be false. So this will run infinitely forever until I stop the program manually. Next up, we have count control loops. So most programming languages provide a for loop for this situation, and a for loop uses a counter to store the number of iterations. And so we have initialization, test, and increment. And so we'll initialize, right? So here we're initializing the counter, constant integer max value 5. And so from 1 to 5, keep displaying this. So this is a classic for loop. we declare the integer counter first, we set the counter, or we set the max value, and then we run the counter up to the max value. You also don't have to declare this. You could just put 5 here, and then it'll just run from 1 to 5. Next up, programmers need to know the exact number of times. Do not need to know the exact number of times a loop will run, because you could just set it to a variable, and that variable could be holding whatever value, and that could come from a different program. So we do not need to know the exact number of times a loop will run. We just set it to a variable. So a counter is a variable that is incremented, and so in this case, counter will be bumped up every time. But then we also have accumulators, which is earlier. Set k equals 1 is the accumulator. In this case, k was the counter and the accumulator, but sometimes we use 2 different variables. So whatever is being added in a loop is an accumulator, so a variable that stores the sum of elements. Lastly, so for and while loops are considered pre-test because the condition is tested prior to the processing, as opposed to post-test, which is a do while is a post-test. All right, where was I? Pre-test. Okay. Input validation, and so they're also called error traps or error handlers, because you're testing the information given to us by like a user or another program. And so we always want to do input validation because it's garbage in, garbage out. So if we get bad data, our program is gonna, not have satisfactory results unless we sanitize and validate that data that's coming in. Computers cannot tell the difference between good and bad data. If a program reads bad data as input, it'll produce bad data as output. And a lot of hacking incidents can take place if you're not sanitizing or validating that data. All input should be inspected before processing, because we can't trust the data that's being given to us. A priming read in a loop is the first input to be tested, and so it's the first condition that'll be tested. So when you set a counter to 1 and then you put the counter in a loop, 1 is the priming read right here. So this line right here is a priming read. Sentinel is where the end of values is, so that's where a loop will stop. And so if you're gonna, run this loop from 1 until 3, this is kind of the sentinel value. So greater than 3 is the sentinel value. So the sentinel value is actually 4 for this loop. So that's like the value or number that it's looking for to hit before it can stop processing. So you can use that at the beginning to check to see if there's another value to process, or at the end to check to see if there's another value to process, or at the beginning to see how many times the loop will process. Lastly, defensive programming. So input validation is a type of defensive programming. It's the practice of anticipating both obvious and unobvious errors that can happen. And you can get an empty input where a user accidentally hits enter before entering the data. That's bad input, or they enter the wrong type of data. Either way, you need to be cognizant on your end to make sure that we're not processing that bad data. And that's all I have for this review. Best of luck on the exam.